what we are going to do is, we already looked at certain aspects of the data, certain ideas about correlation and scatter plots and things like that. All right. And we also mentioned curse of dimensionality, or what kind of issues having too many dimensions can give rise to. All right. So let's look at what we mean by dimensionality reduction and what are the different techniques that we can use. All right. So what is the purpose of dimensionality reduction? Number one, avoid curse of dimensionality, which I mentioned earlier. What we mean by that? Reduce amount of time and memory required by data mining algorithms. Because what you want to do through dimensionality reduction is to reduce your data size overall. So if overall you're going to reduce the data size, obviously you will have less storage needs, and computationally also you will benefit. Also, by dimensionality reduction, you can do visualization of data from a different angle. See, the last example of data visualization I talked about, basically we looked at data in terms of scatter plots, in terms of histograms and things like that. All right. Suppose you want to see how the whole data is distributed in the high dimensional space. There is no way to visualize distribution of data in the high dimensional space. But what one can do is, one can apply some kind of mapping through dimensionality reduction to project that data from high dimensional space to a lower dimensional space, for example, in a two-dimensional space. And then you can look at the entire data set in a two-dimensional space after mapping. And that can give you, again, some good idea about how your data is distributed and what some of its properties are. All right. And also, by doing dimensionality reduction, what you can do is you can get rid of some of the irrelevant attributes or features, or even reduce the amount of noise that your data might have. Okay. Because sometimes when you are designing a system and in the beginning you're thinking of all kinds of measurements, all kinds of attributes you want to collect so that you can build a good model. But some of those attributes may not be really useful. In that case, there's no point in carrying them on. All right, it's better to discard them. So all those things are possible when you apply one or other dimensionality reduction technique. All right. What we are going to do is we are going to look at several techniques. The first one we will talk about is PCA, which stands for Principal Component Analysis. Then we will talk about SVD, which stands for Singular Value Decomposition. And then we will talk about a nonlinear technique called TSNE, which is meant for visualizing the data by projecting it from a high dimensional space to two dimensions. And of course, when you look at these techniques, some of the techniques can be called supervised techniques, which means you are looking at the data as well as the dependent variable. Some of the techniques are unsupervised techniques where you don't need to worry about the dependent variable. All right. So that's what we are going to be doing. So let's start with PCA, or Principal Component Analysis. Let's look at this data here, all these pink points. Now, if you look at these pink points, which are in two dimensions, by looking at them, you can say that these points are kind of lying around a line which is shown in green in this picture. All right. And these points are moving up or down this line in a normal fashion. So some points are a little up, normally up in a perpendicular direction. Some points are a little down from this line, but more or less all these points are kind of scattered around this particular line. All right. So this line is called the principal direction of the data. That means this line represents the direction in which this particular data set is showing most variability. So the goal of PCA is to find a projection that captures the largest amount of variation in data. And such a projection can be then used to represent your data in a least square sense. So if I take this example and replace every point by its value that gets projected on the line by throwing down a perpendicular or by moving in a perpendicular direction towards the line, then all those points after projections will define an approximation for this two-dimensional data. And that approximation is the best approximation that is possible in a least square sense. So that is what the PCA tries to do. It tries to approximate your data in a least square sense. And by doing the approximation, for example, in this particular case, you don't need to worry about horizontal and vertical coordinates for every point. All you need to specify is the location of that point on the line. And location of a point on a line requires only a single number. That means from 2 dimensions, you are coming to 1 dimension. So you can represent this collection of 2-dimensional points by a collection of respective 1-dimensional points. Obviously, anytime you go through a process where you are going from a high dimensional space to a lower dimensional space, there is going to be some error or some loss of information. So that's going to occur here. But what this technique does is that it tells you that if you follow this method, then the loss of information or the amount of approximation error that you will get is going to be minimum possible. Okay, so that is what the PCA is all about. All right. So question is, how do we figure out or how do we apply PCA? What are the steps in terms of applying PCA? So PCA generally is figured out by looking at the covariance matrix. So first step you will do for a given problem is to calculate the sample covariance matrix. That is the covariance matrix based on the data that you have. So that's why we call it sample covariance matrix. All right. And then we will extract eigenvectors of this covariance matrix. And it turns out that the largest eigenvalue and the corresponding eigenvector. So the corresponding eigenvector will tell us the direction in which the data is showing most variability. And the eigenvalue will give us an indication of what is the amount of that variability. So basically, by looking at the eigenvectors of the covariance matrix and by looking at the eigenvalues of the covariance matrix, we get an idea what is the direction in which the data is showing most variability and what is the level of variability. And of course, if you have a multi-dimensional data, or even for this two-dimensional example, you will have two eigenvectors, one corresponding to the largest value and the other one corresponding to the next value, which is going to be the smallest value in this case. All right. And remember, these eigenvectors are orthogonal to each other. They are perpendicular to each other. All right. So if you look at this picture here, basically, again, this line that I have drawn right in the middle of all these points, that is the line that represents the eigenvector corresponding to the largest eigenvalue. And if I draw a perpendicular line to this line, that will be the second eigenvector corresponding to the next eigenvalue, because we will have, it's a covariance matrix 2 by 2. So we will have two eigenvalues and two eigenvectors. So if you look at original data, let us say you have this original data in 2 dimensions shown in the top left panel. If we apply PCA to this data, basically we will get two principal directions shown as component 1 and component 2 in the leftmost panel. All right. Now, typically what is done is that using the largest eigenvector, or the component number 1 in this particular case, we can rotate the data set so that its x-axis is aligned with component number 1. So that is what we have done in the second panel on the top right hand side. All right. And if we were to calculate one-dimensional projections for all the points, then those one-dimensional projections are going to be shown in the first principal component, and from there we get feature number 1. All right. So basically what you are doing is you are calculating these principal directions, largest eigenvector, next eigenvector, and so on and so forth. And generally you apply some kind of transformation or rotation so that you are talking in terms of, axes that are aligned with horizontal and vertical, etc. And then you get your resulting numbers after transformation. So let's look at what are the steps involved. I showed you visually how it is done, but that was for 2 dimensions. So how are you going to apply PCA for a problem which has many, many dimensions? All right. So what are the steps? So let us assume that the number of features or attributes is small n. So you have n variables. Let's call them as x1, x2, all the way up to xn. So what the PCA does is that it takes these n variables and finds linear combinations of these variables. And through linear combinations, it transforms these variables into a new set of variables, which you can call them as y1, y2 up to yn. And while it is doing this transformation, it ensures that these new variables are uncorrelated with each other. So any correlation that exists among the original features through transformation is removed. when you are defining your new variables or new features. All right. And of course, these new features y1, y2 up to yn typically are indexed in such a way that y1 shows the largest amount of variation. That means y1 corresponds to the largest eigenvalue and corresponding largest eigenvector. Y2 has the second largest amount of variation, and so on and so forth. All right. Now, if you keep all the transformed variables y1 to yn, what you have done is you have transformed your original space into a new space. In the original space, you had n attributes x1 to xn. In the new space also, you have n attributes y1 to yn. So you have not done any dimensionality reduction. What you have done is you have just simply done the transformation. But in practice, what happens is, or what people do is, that out of y1 to yn, people will typically keep only maybe y1, y2, and y3 and ignore the rest of them or discard the rest of them. In that case, in your transformed space, you have only 3 features or 3 attributes. That means you have gone from n attributes, where n could be 10 or 20, and you have come down to 3 attributes or 4 attributes. So obviously you have achieved a great deal of dimensionality reduction. And if you look at the way we have defined y1, y2, etc., y1 is the variable, new variable, which has most variability. Y2 is the variable which has next most variability. Y3 is the variable which has next most variability. All right. And if you look at yn, yn is the variable that has the smallest or least amount of variability. So if there is a measurement that really does not vary much, you can safely discard that measurement, because since it is not varying much, it's not giving you any information. So you can simply throw it away. So that's the reason. That is, you keep only top few variables which account for most of the variability in your data, and you throw away the rest of the variables because they account only for a very small amount of variability in the data, and consequently, they are not likely to contribute much to your model. So that's the basic idea of PCA. And PCA is also known as KL transform or Karhunen-Loew transform. It is also known as Hotelling transform or eigenvector analysis. These are all different names for the same thing. All right. An interesting application for PCA came somewhere around 30 years ago. It became very popular. And this is known as an eigenfaces. That is what it was shown, is that you can represent, suppose let's look at Michigan Secretary of State. All right. What they do is they basically have your picture because they have it on your driver's license. All right. So they have pictures of everybody who is a driver in the state of Michigan. All right. So if you take that collection of pictures and perform PCA kind of operation and just extract top 20 eigenvectors, which represent, in this case, since each vector is representing a face, you can call them as top 20 eigenfaces. Then what you can do is you can reconstruct each and every driver's picture using those 20 eigenfaces by mixing them with different amounts of weights. It is just like you have 3 primary colors, red, green, and blue. You mix them in different amounts, you get variety of colors. All right. Same thing, you can take a large collection of faces, apply PCA, extract eigenfaces, keep some of the top eigenfaces, and use them to reconstruct. All right. So that's what is being shown here. That is, through PCA, each face on the left can be represented as a weighted linear sum of eigenfaces. All right. So that's an interesting example or application of PCA that became very popular. And why this was popular, many years ago? Because these eigenfaces that you have extracted and you are using, these eigenfaces are standard in the sense that we know for the state of Michigan, everybody's face can be reconstructed using these eigenfaces. All right. So one need not carry these eigenfaces for individual person's record. To encode a particular driver's face, all you need is what are the weights in that linear sum, because just like red, green, blue, this component is fixed. So you don't need to carry that. All you need to do is to specify for every person what are the 20 weight values that we will use to reconstruct that person's face. That means everybody could be identified using 20 numbers. So this could be used for identification of persons using 20 numbers. All right. So that was the idea that caught on. And of course, since then, there are more sophisticated techniques and things like that. But that gives you an idea of how this PCA could be used not only for dimensionality reduction, but you can turn it around and use it for a number of other interesting applications. All right.